All right, so linear programming is a process involving systems of inequalities, okay? And what you are doing in this process is you are finding maximum and minimum values of what's known as an objective function over a feasible region, okay? None of that means a whole lot to you in the moment, but give me a few minutes and it will, okay? All right, so consider the solution to the following system. X greater than or equal to 1, y greater than or equal to 0, 2x plus y less than or equal to 6. Okay, so that's a system of inequalities. The solution to it would be the overlap of the shaded region, which I already have graphed over there on the right. That's that triangular region. Okay. We're going to consider the inequalities of the system. We're going to start to call them constraints. Okay, these are the constraints of the system. And then your solution to that system, we're going to now call it the feasible region. The feasible region. Okay. So linear programming, again, is the process of maximizing or minimizing a function over a given region. And here's the key. The maximum or minimum value of the related objective function, it will always occur at a vertex of the feasible region. At a vertex. And I'll give you a nice visual here in a few moments as to why it is that way. Okay, but for now, just kind of take my word for it. All right. So let's get right into an example here. Graph the following system of inequalities, name the coordinates of the vertices of the feasible region, and then find the max and min values of the function for this region. All right, so your constraints, again, those are your inequalities of the system, okay? So x less than or equal to 2, that would be a vertical boundary line that is solid right here. And I would shade to the left of that, correct? Now let's color code this. I did my first one in blue, so now I'll do my next one in red. Y is less than or equal to 3. That would be a horizontal boundary line that's solid. I'd shade below it. And then y is greater than or equal to negative x plus 3. Y-intercept at 3. Slopes negative 1. Another solid line. Okay, and if you used a test point on that, you'd end up with 0 is greater than or equal to 3 if you use the origin, which is false, right? So for that one, I would shade on this side. Okay, so the overlap of all those, kind of hard to see because I didn't do very much shading, but the overlap would be this triangular area right here. And that's my feasible region. And notice that region has 3 vertices. Okay. Now let's make a table. In this table, I'm going to have a column for all of the vertices, and then I'm going to have a second column represented by the objective function, okay? So my vertices are 0, 3, 2, 1, and 2, 3. All right, now look at the objective function here. It says f of x comma y equals 2x plus y. So this is a new notation for you. You haven't seen that before probably. You're just used to f of x, right? Not f of xy. So think about it. F of x is function notation, and what does f of x really represent? What's it stand for? It's a y, right? So what do you think f of x comma y would stand for? What do you think? It can't be y because notice it's this function is equal to 2x plus y. Thoughts? F of x comma y, what's another way of representing that? No one? How about z? This is just like a z value. So the objective function we're working with here is actually a three-dimensional equation, okay, that represents a plane, all right? So what we're going to do is take the coordinates of our vertices, which are an x-coordinate and a y-coordinate, we're going to plug them into that formula, 2x plus y, and the result that I get from that will be considered a z value, okay? So f of 0, 3, that would be 2 times 0 plus 3, which wouldn't that result in 3? Then f of 2, 1, that would be 2 times 2 plus 1, which would be 5. And f of 2, 3 would be 2 times 2 plus 3, which would be 7. And once we get those three results, we just ask ourselves, out of those three numbers, 3, 5, and 7, which is the smallest? 3. So that means 3 is my minimum value. And here would be a really good way of writing your answer. You're going to say minimum of 3 at the point 0, 3. Now, out of those three results, 3, 5, and 7, which one is the largest number? 7, of course. That's your max value. So we'll say we have a maximum value of 7 at the point 2, 3. That's what we're after. Okay? So I think this is one of those concepts that, like, procedurally, it's not that difficult to do, but you might be conceptually not following what we're actually doing here, okay? So this illustration I'm about to show you, I think, really can help us to conceptualize this, all right? Because we're working in both 2 dimensions and 3 dimensions here. The constraints have been graphed in 2D, but then that objective function represents 3D, okay? So here we go. Let me open this up. Oops. Okay, so in this illustration, the left side of the screen is 3 dimensions, and the right side is 2 dimensions, okay? And I'm going to manipulate this to look like our region. So let's see, we had 0, 3 as one of our points, 2, 1, and 2, 3. Everything's being slow on me today. All right, looks similar to the region we graphed. Yeah. And then what was it? Z or f of xy equaled, was it 2x plus y? I'm just going to make this a 2. Notice when I change that value, it's going to change the equation over on the left side of the screen there. Okay, so notice I have z equals 2x plus 1y graphed on the left here. That's that gray plane. Okay? And then you can see within this illustration, you have the xy plane also shown there with that region, the feasible region, right? What we're doing when we are working in a linear programming problem is we are taking that feasible region, and in a sense what we're doing is we are projecting it up into 3 dimensions to see where it intersects this plane, okay? So watch the illustration on the left here as I move this slider. I'm taking and projecting that region up and seeing where it intersects the plane that I'm working with that's represented by the objective function. You see that? And then notice I have this blue point that's inside the feasible region, right? I'm going to also project that point up as well till it intersects the plane. Okay? You can see it's that yellow point there. And I can move this point. When I move it to this vertex right here, see how that's the lowest point out of the green region in that illustration. And if I were to move it over to here, that is now the highest point, right? But if I have this anywhere that's not at a vertex, it's not going to be the lowest or the highest point. Does that make sense? Okay. So again, we got the lowest point to be at 0, 3, and then the highest point to be at 2, 3, which matched our 2 answers, right? So that's what you're doing when you are solving a linear programming problem. You're looking for those high and low points of that 3-dimensional region. Make sense? Okay. So now let's do example 2. Same directions. Constraints are a little bit more challenging to work with this time, okay? All right, so let me do this one in blue. Negative x plus 2y less than or equal to 2. That's going to have an x-intercept of negative 2. And it's going to have a y-intercept of 1. So the slope there is 1/2. And that would be solid. Origin is going to lead me to 0 is less than or equal to 2, which is true. So I would shade underneath of that. Next one I'll do in red. X-intercept is 4. Y-intercept is negative 2. Slope on that's up to right 4, which reduces to 1/2. So notice those 2 lines are parallel to each other, right? And for that one, if I use the origin as a test point, I'd get 0 is less than or equal to 4, which is also true. So for the red, I'm shading above it. Right now, the overlap's in between the 2 parallel lines, right? Okay. Last one, x and y intercept are both at -2. Where the slope's -1. Another solid boundary line. And the origin for that's going to give me 0 is greater than or equal to -2. Yet another true statement. So the shading would be here. So your feasible region ends up being this section. All right, now notice this time that region, it's what we call an unbounded region. Okay, it's not completely enclosed, right? Isn't it going to keep going in this direction? Okay, so you only end up with 2 vertices here. This point and this point. So let's make a table like we did on the last problem. Left side of the table represents the coordinates of the vertices, and then the right side will represent the z value that those give you with the objective function. Okay, so the points are 0, -2, and -2, 0. So f of 0, -2 is just going to lead you to -6, and f of -2, 0 is going to lead you to -4. Okay, and we're trying to do the same thing as the last problem. We're trying to find a max value and a min value, right? So there's only 2 points here, so it stands to reason that the smaller value out of the 2 should be my minimum, and then the other one should be my max, right? Well, that's not correct. On an unbounded region, typically you don't have both a maximum and a minimum. It's one or the other. Okay? So let me try to visualize this for you. It's all predicated on the plane that's represented by that objective function. Okay? All right, so that looks kind of sort of like our region, right? So right now, think of it, it's on 2D, it's in 2D in the coordinate plane, okay? I project this up until it intersects the plane that's represented by this function, okay? Now, depending on how that function or how that plane is positioned in coordinate space, that's going to determine whether we get a max or a min, okay? So I project it up. Now let's treat the white piece of paper like it's my plane, okay? If I project it up and the plane is positioned something like this, see how that region would keep moving upward. There would be no high point to it. And that means the low point would be right here, okay? So I'd have a minimum value at this point, okay? Now, I don't have a graph of this, though, so I don't really know what it looks like. I don't know how it's positioned in coordinate space without actually graphing it, okay? So it could be completely different than how I have it right now. It could be like this. Now I would say there's no minimum, right? And instead of max, right? It's really involved to try to graph this in coordinate space on a 2D piece of paper. We can do it, but it's just really hard to kind of visualize then the intersection with that feasible region. So here's how we figure out whether we got the max or the min. We use a test point, okay? your test point has to come from the feasible region. Okay? So anywhere in my yellow region, I'm going to pick a point. So how about I do something simple like 1, 0? Would we agree that's in my feasible region? Now, what would f of 1, 0 result in? It would give me 2. And notice how 2 is bigger than both of the results from the vertices. So what we have here is a non-vertex giving us a larger value than either of the vertices did. My conclusion off of that is there's no maximum then. Okay? So let's label a couple of things here. First of all, let's say this is a test point coming from the feasible region. Did I have to use 1, 0? Of course not. I could have picked another point as long as it was in the region. Okay? And what I can say here is that this is my minimum value, -6. I have a minimum of -6 at the point 0, -2. And then I would say there is no maximum value since a non-vertex from the feasible region resulted in a larger z-value than either vertex. Now, you don't have to write all of that out every time this situation comes up. I just did it for the sake of our notes when you go back and you look at this, okay? So just all you'd have to say is there's no maximum, okay? Now, sometimes the test point that you pick ends up being inconclusive, okay? If your test point gives you a number that's between the values that the vertices gave you, then that's inconclusive. You're looking for the test point to give you a result that's bigger than any of your vertices or smaller than all of your vertices gave you. Okay? So sometimes you might have to use more than one test point. Questions on that? No? Okay. So try practice 1 for me really quickly. The nice thing about this is the constraints are already graphed. It's a bounded region, so we shouldn't have to worry about these test points. And we're just trying to maximize and minimize the given objective function. Just take 1 or 2 minutes to work through that. One more minute. Oh no. Yeah, you might need your car keys. Yeah. Yeah, it's from my class actually. So.
I think Austin did too.
Did he?
Yeah, I might get one. I still have 2 kids that I think just tested positive.
Okay. All right. Let me know. All right. What would f of 0, 0 give you? Boom. How about f of 0, 2? Not 0. 8. And f of 4, 0? Negative 8. Okay, so since this is a bounded region, you got to have a max, you got to have a min. Okay? So the max would occur right here. Min would occur right here. All good? Okay. So for homework, there's another numbers file that says linear programming practice. Okay. You're going to do the first 4 problems out of that file. The second half of that, those are all word problems, and we're going to save those for Wednesday after our quiz, okay? So we're just doing 1 through 4 and preparing for Wednesday's quiz over 3D graphing and solving 3x3 systems. Any questions?